Hi everyone, welcome back. So, what do we have here? We're going to do another problem, once again dealing with carburization, but in this time, we're actually getting rid of carbon. And so this is going to be decarburization. And also through this problem, we get a little bit of experience with the error functions. If you've not used it very much before, well, this will help you out. So, let's run through it. An FCC iron carbon alloy initially contains about 0.35 weight% of carbon. It's exposed to an oxygen-rich and virtually carbon-free atmosphere. So the carbon concentration at the surface is 0. And it's at 1400 Kelvin, pretty hot. Under these circumstances, the carbon diffuses from the alloy, reacts with the oxygen in the air, and turns into carbon dioxide or carbon monoxide and just disappears. And so that means that we're going to be reducing the amount of carbon I have in my alloy over time. So, at what position will the carbon concentration be 0.15 weight% after a 10-hour treatment? And it gives us the value of our diffusion coefficient, making it really easy on us. So this is not that hard of a problem. The big thing is we have to realize how carbon concentration with position is affected. So we have this equation we use a lot, which is simply saying my carbon concentration at a particular position minus my carbon concentration initially over my carbon concentration at the surface minus my carbon concentration initially is equal to 1 minus the error function. And the error function is simply showing us how position, diffusion, and time are all related. Okay, so of these aspects, we know a lot of this. First off, we know the carbon concentration at the surface. Why? Because it tells it to us. It says it's roughly 0%. We also know the carbon concentration initially. We know the carbon concentration at that point that we want. We're going at 0.15 weight%. We know the diffusion coefficient and the time. And so if you look at this, we know everything except for our position. And so we can solve this fairly easily. So let's go ahead and solve for what the error function value would be. I'm going to plug everything in here. So I've got 0.15 minus 0.35. Try to make those periods a little bit bigger, over, let's see, 0 minus 0.35 is equal to 1 minus the error function. And I'm just going to call this guy inside of it z because that's usually what your book shows you. And so what I get then is that my error function, z, is equal to 0.4286. So like, okay, how do I unearth my function so I can get, solving for x? Well, you can't do it by yourself. This is a complicated equation, and what you have to do is you use tabulated values. So in the table, you'll find two columns. You'll see z and you'll see erf z. Z being what's inside the function, erf z being the value of the function with what's inside of it. So we calculated erf z to be 0.4286. If I look at my tables, I will not find 0.4286. I'll find, let's see here, 0.4284, and I will find 0.4755. That's the closest I can get here. And on the other side, I'll see 0.4 and 0.45. So how do we solve? How do we solve for what our z value would be if it was at 0.4286? The answer? Interpolation. Okay? Interpolation. So all you're assuming here is that, one, I have some values. So this is erf z. This is z. And I'm assuming that it's some function. I know these 2 points. I have my point in the middle. And what I'm saying is, okay, the slope between these 2 points is the same as the slope between these 2 points. Those should be the same. Is that true? No, not necessarily, but for small enough step sizes, the errors will be really small and we can do a lot with it. So let's use that to solve it here. So we're going to develop the slope equation between these 2 points, and we're going to do the same thing but between these 2 points and set them equal to each other. So rise over run, okay? I'll say in this case, since I want to solve for z, that z is my rise and the erf z is my run. So first for the 2 values. So z minus 0.4, that's the rise over the run, 0.4286 minus 0.4284. Okay, so that should be equal between to the slope between these 2 points. So once again, the z values are my rise, they go on the top. So 0.45 minus 0.4 over 0.4755 minus 0.4284. That's all you're doing. There's lots of ways of writing this linear interpolation equation, but you're just saying the slopes are the same. That's the easiest way to probably to remember it. And then you just do a little bit of algebra to get it by itself. So when I solve this, I get that z is, who would have guessed, very, very close to 0.4, 0.4002. I really could just guess that from the beginning because these two values are so close that I could have said, you're close enough, I'm just going to say 0.4. I wanted to show you some interpolation though, which is why I didn't. So that's my value of z. And what we realized was that z was equal to everything inside of the error function. So x over 2 square root of dt. And I know all those values, except for x. So I can go ahead and solve this. One of the things we're going to have to do though is my time, if I go back up here, was 10 hours. And so I'm going to need to convert that into seconds. That's not hard. A good conversion to memorize is that 1 hour is equal to 3,600 seconds. And so 10 hours would be equal to, you guessed it, 5 seconds. Okay, 36,000 seconds. So let's plug everything in and we'll get our value for x. So let's see here. X is going to be equal to 0.4002 times 2 times the square root of my diffusion coefficient, which was given, which is 6.9 times 10 to the negative 11th, times that time in seconds, because our diffusion coefficient was in meters squared per second. So my time has to be in seconds, which is 36,000 seconds. And I get a distance, let's see here, of 1.26 times 10 to the negative third meters. It's really small, so let's go ahead and convert that to millimeters and be equal to 1.26 millimeters. If you're wondering how did I know what unit it was going to be when it popped out, it's because this was meters squared. The square root of meters squared is equal to meters. That's it. So for this problem, we have solved it. We've gotten our use our error function to find the value of z, and from that we're able to find the distance within my alloy where this carbon content had dropped to this point. So thank you so much. I hope this helps you. And once again, if you aren't a member yet, please consider becoming a member to help support my channel. It helps me to have more time to make more videos and more example problems for everyone else. So thanks for watching. See you all later. Bye-bye.